Hello and welcome to the Sleepy Science Channel. Tonight we step gently into the astonishing and ancient world of dinosaurs. Creatures so diverse and so successful that their legacy still shapes life on Earth today. These animals were far more than the movie monsters we often imagine. They were hunters and parents, travelers and survivors. Each species adapted to a particular way of living. Some were built to thunder across open plains. Others evolved for quiet feeding, for social display, or for patient ambush. Their bodies tell stories of strength, speed, intelligence, and transformation. Dinosaurs were not all enormous giants, and they were certainly not all alike. They existed in countless forms, from feathered runners to heavily armored tanks, from towering long-necked browsers to sharp-eyed predators. Their bones preserve moments of struggle, growth, care, and endurance. Even today, their legacy continues through the science that slowly uncovers their lives. If you enjoy these calm journeys into the natural world, feel free to like, subscribe, or share a thought below. It helps others discover this quiet corner of science as well, one sleepy soul at a time. But for now, there is nothing you need to do. Allow your breathing to slow. Let your body soften. Let your thoughts begin to settle. And join me as we begin this long, gentle journey into a prehistoric world. Let's begin. Dinosaurs ruled the Earth for more than 160 million years. That span of time is so immense that it is difficult to truly imagine. Entire groups of animals appeared, evolved, and vanished, while dinosaurs continued to thrive. They lived through ages when seas flooded across continents and later retreated again. They witnessed forests shifting, deserts expanding, and coastlines reshaping themselves again and again. Across this long reign, dinosaurs did not remain the same. They diversified into sprinters, giants, grazers, diggers, and hunters. Their bodies reshaped as environments changed, and new species appeared like new chapters in an endlessly unfolding story. Whenever you picture a dinosaur, you are really picturing just one moment from an enormous timeline. Their story stretches across deep time, long enough for evolution to run countless experiments and refine success again and again. Birds, in fact, are living dinosaurs, and in that sense, dinosaurs never truly disappeared. If you watch a bird hopping across a garden or gliding between trees, you are seeing a survivor of an ancient lineage. This connection is not poetic imagination. It is written directly in bones and behavior. Many birds possess wishbones like their dinosaur relatives. Their ankles and toes follow the same structural plan. Nest building, brooding, and parental care echo patterns preserved in fossils. Feathers themselves did not suddenly appear when birds began flying. They belong to a far older story that began long before flight. In other words, extinction did not close the chapter of dinosaurs. It narrowed it. One branch endured, and from that branch came the birds that now fill our skies and forests. Every bird call you hear carries a faint echo of a world filled with claws, crests, and long shadows. Dinosaurs were not simply giant lizards. Their limbs stood upright beneath their bodies, much like ours. This posture changed everything about how they moved. Instead of sprawling legs that pushed outward, their hips and knees aligned directly under the body. This allowed more efficient walking and running, while also freeing the lungs and ribs from being compressed with each step. It also allowed some dinosaurs to reach enormous sizes because their skeletons could stack weight in strong vertical columns. Imagine the contrast. A crocodile must drag its heavy body forward with its belly close to the ground. Many dinosaurs, by contrast, walked with their bodies lifted high, their strides longer, and their heads held above the landscape. This posture allowed some species to become fast pursuers, while others became steady travelers, capable of crossing great distances. It is one reason dinosaur footprints feel so alive. The tracks appear purposeful, balanced, and directed, not sprawled across the ground. Some of the largest sauropods may have outweighed a fully loaded Boeing 747. To support such tremendous living weight, nature built them almost like moving bridges. Their leg bones were thick pillars. Their hips were broad and powerful. Their feet spread weight across wide pads that distributed pressure into the ground. Yet these giants were not clumsy creatures. Their long necks allowed them to feed across wide areas without constantly moving their massive bodies, saving precious energy. Their tails balanced this length, while their bodies worked like enormous biological factories, turning leaves into muscle day after day. When paleontologists estimate their weight, they are not guessing randomly. They compare limb strength, body proportions, and known physics from living animals. The result is an animal that almost challenges our sense of what is possible. Sauropods remind us that Earth once supported giants so immense they might seem impossible if we had not discovered their bones. Yet not all dinosaurs were large. Some were smaller than a chicken, quick, agile, and elusive. This is the side of dinosaur life that films often overlook. Small animals can hide, dart through dense vegetation, and exploit food sources that larger creatures cannot reach. A tiny dinosaur might chase insects through the undergrowth, snatch small prey, or escape danger in a flash of speed. Small bodies also mean rapid generations, which can accelerate evolutionary change. Some of these animals likely lived in the shadow of much larger species, surviving simply by being difficult to notice. Their fossils are rare, not because they were uncommon, but because delicate bones break and scatter more easily. When scientists discover a small skeleton, it can reshape our understanding of an entire dinosaur community. Suddenly, the landscape becomes richer and more complex. Dinosaurs were not only kings of the land. Many lived fast, alert lives in the margins, where the world was crowded, unpredictable, and constantly in motion. Tyrannosaurus rex possessed one of the most powerful bites ever developed by a land predator. But that incredible force did not come only from sharp teeth. It was the result of an entire biological system built specifically for strength. Its skull was heavily reinforced. The jaws were deep and broad, and enormous muscles anchored across wide surfaces of bone, allowing the animal to generate tremendous pressure when it closed its mouth. The teeth themselves were not thin slicing blades like those of many predators today. Instead, they were thick, strong, and shaped more like crushing spikes. This structure made them far better suited for penetrating hard material. Fossils from other animals sometimes preserve deep punctures and shattered bone that perfectly match the size and spacing of Tyrannosaurus teeth. Evidence like this suggests a predator capable of breaking through parts of prey that other hunters might have avoided. A bite like that changes the rules of a hunt. Instead of slowly wearing down a victim, one powerful strike could cause immediate catastrophic damage. It also allowed Tyrannosaurus to access marrow and other nutrient-rich tissues hidden inside bones. This is one reason the animal still inspires such awe. Tyrannosaurus rex was not simply a hunter. It was a predator capable of overpowering the very structure of its prey. Many dinosaurs also grew at remarkable speeds, reaching adult size far faster than scientists once expected. One of the great surprises hidden inside fossil bones is the evidence of rapid growth. When paleontologists examine thin slices of dinosaur bone under a microscope, they sometimes see textures linked to very fast deposition of new tissue. In practical terms, fast growth can be a powerful survival strategy. A young animal that grows quickly spends less time small and vulnerable. The faster it reaches a larger size, the sooner it becomes harder for predators to attack successfully. Rapid growth can also help populations recover after difficult seasons because individuals reach breeding age sooner. Yet growth was not identical across all dinosaur species. Some appear to have grown in dramatic spurts, almost like teenage growth phases. Others followed steadier, more gradual paths. Scientists can even observe lines within bones that reflect temporary slowdowns in growth. These lines may represent periods of stress, illness, or limited food availability. In this way, each fossil skeleton becomes something like a biography written in mineral form. The bones quietly record the life history of the animal, moments of abundance, moments of hardship, and the rhythm of growing through changing seasons. This evidence also challenges an old stereotype. Dinosaurs were not sluggish, slow-moving reptiles. Many were energetic, rapidly developing animals that grew quickly and lived active lives. Dinosaurs also lived on every continent, even in ancient polar regions. This might sound surprising at first. Today, we imagine dinosaurs inhabiting warm jungles and wide plains. Yet fossils discovered in high latitudes show that dinosaurs lived even in areas that are now polar landscapes. During the dinosaur era, polar regions could be milder than they are today. Even so, these environments still experienced long periods of seasonal darkness. Evidence suggests that dinosaurs did not simply pass through these regions temporarily. They lived there. Surviving in such places would have required resilience. Some species may have migrated seasonally. Others may have relied on social behavior, thick coverings, or specialized metabolisms to cope with cooler conditions. This discovery dramatically expands our understanding of dinosaur adaptability. They were not confined to one type of environment. Instead, they occupied river plains, coastal wetlands, forests, deserts, and even far northern or southern lands. Their bones and footprints appear in rocks all across the globe, telling the story of a group of animals that succeeded on a planetary scale. When you imagine a dinosaur standing beneath the dim light of a polar winter, it becomes clear just how flexible these animals truly were. They were not creatures of a single landscape. They belonged everywhere. Fossil footprints can preserve moments of life with extraordinary immediacy. A footprint is a direct physical contact between the past and the present. Millions of years ago, an animal stepped into soft ground. Sediment later hardened around that impression, preserving it for ages. Unlike bones, footprints often reveal behavior in motion. Tracks can show where an animal turned, where it paused, or where it suddenly accelerated. Some trackways stretch side by side across long distances, suggesting groups moving together across open land. Others show a lone animal pacing along a shoreline, leaving a sequence of steps that reveal its stride and rhythm. Footprints can also preserve small details, such as the spread of toes or the marks left by claws. These clues help researchers identify which type of dinosaur made them. But trackways offer something even more fascinating. They record decisions. A trail of footprints shows where an animal chose to walk, what terrain it crossed, and how it navigated its world. Standing beside dinosaur tracks can feel almost uncanny. You are standing beside the frozen memory of a walk that happened tens of millions of years ago. Eventually, a single catastrophic event helped end the age of most dinosaurs. About 66 million years ago, a massive asteroid struck Earth near what is now the Yucatan Peninsula. The energy released by that impact was enormous, far beyond anything humanity has experienced. Dust and aerosols were blasted high into the atmosphere, spreading around the planet and blocking sunlight. Without sunlight, plants struggled to survive. As plants declined, entire food webs began to collapse. Herbivores lost their food sources. Predators soon followed. This extinction event, known as the End Cretaceous extinction, removed many dominant groups of animals from Earth. Yet it did not erase life entirely. Some species survived, and from those survivors, entirely new ecosystems eventually emerged. The asteroid impact reminds us that life on Earth is shaped not only by biology, but also by geology, climate, and cosmic events. Evolution does not unfold in isolation. Sometimes the forces that reshape life come from the sky. The extinction of the dinosaurs was not simply an ending. It was also a reset, a moment that opened new ecological spaces for the creatures that remained. And among those survivors were the ancestors of modern birds. Feathers, interestingly, evolved long before flight. At first, feathers were not wings. They were tools for everyday survival. A soft coat of feathers can trap warm air close to the body, helping animals retain heat during cold nights or seasonal changes. Feathers can also serve as signals. Colorful patterns and shapes can communicate strength, health, and readiness to compete. In the animal world, visual displays can settle conflicts without violence. Imagine a small feathered dinosaur lifting its arms and spreading its plumage. Suddenly, it appears larger, brighter, and far more noticeable. In a world where attracting a mate or intimidating a rival can determine success, display becomes incredibly important. Feathers may also have functioned as sensitive instruments. They can detect subtle changes in airflow, helping an animal sense movement around its body. Long before true flight appeared, feathers were already performing valuable roles. Evolution was slowly building the materials needed for a future innovation. Many dinosaurs likely displayed colorful patterns, much like modern birds do today. Color in the natural world is rarely simple decoration. It carries information. Patterns across skin, scales, or feathers can help an animal disappear in shadow, break up its outline among tall grasses, or send signals to others of its kind. Dinosaurs almost certainly relied on these same strategies. Imagine standing at the edge of an ancient forest where sunlight flickers through shifting leaves. A striped body could vanish in that moving pattern of light and shadow. Now imagine a crowded breeding ground where many animals gather together. A bright crest or a bold splash of color might allow an individual to stand out among rivals and be recognized instantly by members of its own species. Even though we do not know the exact colors of every dinosaur, the logic of evolution strongly suggests that color played a significant role in their lives. Predators benefit from camouflage. Social animals benefit from clear visual signals. A dinosaur world filled with color feels far more alive than the gray stone images we sometimes imagine. Some dinosaurs possessed hollow bones designed to provide strength without unnecessary weight. At first, this idea may sound fragile, but in reality, it represents a remarkable engineering solution. Hollow bones are not empty tubes. Inside them are internal supports and braces that strengthen the structure against bending and twisting. Modern birds use this same design. Their skeletons remain strong while also staying light enough to support flight. In dinosaurs, hollow bones could have provided several advantages. A lighter skeleton makes movement easier and more efficient. It allows longer limbs, faster running, and sometimes even larger body size without wasting energy carrying extra mass. When paleontologists discover these bones, they see evidence of animals built with remarkable efficiency. Every step an animal takes requires energy. Reducing unnecessary weight allows longer journeys, quicker escapes, and greater endurance during hunts. This reminds us that dinosaurs were not only defined by size, many were shaped by the same engineering principles that guide modern bridges and structures, using the least material possible while still carrying great loads. Many dinosaurs also possessed air sacs throughout their bodies that made breathing far more efficient. Breathing is not simply about filling the lungs. It is about delivering oxygen to working muscles and removing waste gases that cause fatigue. In many dinosaurs, air sacs likely helped move air through the respiratory system in a continuous flow. This kind of system allows oxygen to be absorbed far more efficiently than the simple in and out breathing used by many reptiles. Such a system also helps release excess body heat. Air sacs may even extend into parts of the skeleton, making some bones lighter while also increasing respiratory efficiency. For an active predator, this could allow longer chases without exhaustion. For a massive herbivore, it could help supply enough oxygen to power an enormous body. This type of respiratory system suggests animals capable of sustained activity. It hints at endurance, alertness, and athletic ability far beyond the old image of dinosaurs as slow, lumbering creatures. Their bodies were tuned for power that could last. Dinosaurs laid eggs, but some species also guarded their nests with remarkable care. An egg represents possibility, but it is also vulnerable. The natural world is full of threats: predators, flooding rains, sudden cold, or intense heat. Nesting behavior helps reduce those risks. Guarded nests mean fewer eggs are lost. Careful placement of nests can improve temperature conditions for developing embryos. Some dinosaurs may have chosen nesting sites with great care. Higher ground might protect against flooding. Sheltered areas could reduce exposure to wind. In some cases, multiple adults may have remained nearby to watch for danger. Thinking about this changes our emotional picture of dinosaurs. These were not only creatures of teeth and thunder, they were also animals investing energy in a future they might never see. Parental care is one of the oldest stories in nature. When you imagine a dinosaur returning to its nest, you are seeing a behavior that still echoes through forests, coastlines, and grasslands today. In some fossil discoveries, adult dinosaurs are preserved sitting directly over their eggs. These fossils show a posture strikingly similar to the brooding behavior of modern birds. The adult's body is positioned as if protecting the eggs beneath it. Such an arrangement is unlikely to be accidental. Brooding involves more than guarding. It allows a parent to regulate temperature and shield the eggs from sudden environmental changes. It also deters scavengers that might otherwise steal an egg and disappear quickly. This behavior suggests patience and dedication. Remaining still for long periods requires discipline. It implies that dinosaurs had lives shaped not only by feeding and fighting, but also by waiting, protecting, and nurturing. It creates a scene that almost feels audible. A quiet nesting ground, the soft scrape of shifting limbs, the steady presence of an adult that chooses to remain. Fossils like these are rare gifts. They preserve care, not just bone. Some dinosaur hatchlings were capable of walking almost immediately after emerging from their eggs. Imagine breaking free from a shell into a world where danger is everywhere. For some species, the best defense may have been immediate mobility. A hatchling that can stand and move quickly can stay close to the group and avoid being left behind. It can reach shelter, follow adults toward food, and escape threats more easily. Early mobility suggests a particular style of parenting. Young dinosaurs capable of walking right away may have needed less feeding in the nest. Instead, they relied on guidance, protection, and group movement. The first hours of life would have been intense. Tiny legs learning balance, eyes adjusting to light, instinct pulling the young animal toward safety. This creates a vivid image of dinosaur childhood. Not all young were helpless. Some were born ready to move. Other species likely followed the opposite strategy. Their young remained in the nest longer, protected and cared for by attentive parents. In this case, the nest becomes a center of life. Parents may have brought food, defended the surrounding area, and protected the growing young from predators. This strategy allows offspring to develop strength, coordination, and instincts before facing the wider world. Such care can influence social behavior. If parents invest heavily in their young, family bonds become important. Learning becomes important. Nesting areas may even become locations that animals return to year after year. Raising young requires time and energy. That cost gives the behavior meaning. When we imagine dinosaurs this way, they no longer appear as isolated creatures wandering alone across ancient landscapes. Instead, we begin to see families, relationships, and the patient work of raising the next generation. Sometimes dinosaur nests appear in large clusters, hinting at the existence of nesting colonies. A single nest tells one story, but an entire field of nests tells something much larger, a story about community. When many nests appear close together in the same geological layer, it suggests that this location was used repeatedly, perhaps even by many animals at the same time. Nesting colonies offer certain advantages. Safety in numbers is one of them. Many watchful eyes can detect danger earlier, and a predator approaching one nest may suddenly face a wall of defending adults. Colonies may also help synchronize hatching. If many eggs hatch around the same time, predators cannot easily focus on a single young animal. The sheer number of hatchlings reduces the risk for each individual. A colony site can also hint at memory and tradition. Animals may return to successful nesting grounds year after year, guided by instinct, scent, or the familiar shape of the land. Yet colonies are not always peaceful places. Close neighbors mean competition for space and resources. Disputes over territory may have been common. Still, clustered nests paint a picture very different from the old image of solitary dinosaurs wandering empty landscapes. They suggest busy places filled with life, repeated seasons of nesting, repeated choices, repeated generations growing in the same ground. Eggshells themselves can reveal remarkable information about how dinosaur nests functioned. An eggshell is not only protection, it is also a breathing surface. Tiny pores in the shell allow gases to pass through. Oxygen must enter so the developing embryo can breathe, and carbon dioxide must escape. The structure and density of these pores can reveal the environment in which the eggs were laid. A buried nest, for example, requires a different pore structure than an exposed nest. Soil affects how gases move around the egg. Humidity also plays a role. Moist conditions influence how easily air can circulate. By studying fossil eggshells, scientists can sometimes infer the nesting environment and parenting style of long-extinct dinosaurs. It is almost like discovering the ventilation system of an ancient nursery. Even the smallest holes in a fragment of shell can carry clues across millions of years. The first dinosaur fossils were officially described and named during the 1840s. In the early 19th century, strange bones began appearing that did not resemble the remains of any known animal. Naturalists were beginning to compare anatomy carefully across species. They were also beginning to accept the idea that Earth was far older than previously believed. When the first dinosaurs were described and named in the 1840s, it was like opening a door in a wall that no one realized existed. Suddenly, the rocks revealed a category of life older than human history and more extraordinary than imagination had allowed. These early discoveries did more than add new names to scientific catalogs. They revealed that entire worlds had existed long before humanity. Fossils were no longer odd curiosities. They became evidence in a much larger story about how life changes across immense spans of time. The word dinosaur itself means terrible lizard. It is a dramatic name, and that drama helped capture public attention. Yet the name can be misleading. Many dinosaurs were not closely related to modern lizards at all, and many were not terrible in any simple sense. Some were small, cautious animals that survived by staying hidden. Others lived peacefully by grazing on plants and avoiding danger whenever possible. Even the largest species were not monsters. They were simply animals doing what all animals do: finding food, avoiding threats, and raising offspring. The word dinosaur tries to describe an enormous diversity of life with a single label. In reality, the group includes creatures as different from one another as whales are from wolves. The imperfect name reminds us that language often struggles to keep pace with discovery. Our first impressions are shaped by words. Fossils sometimes demand better stories than those words originally provided. One of the earliest dinosaur discoveries involved a single tooth. At the time, scientists did not yet know that dinosaurs existed. Imagine finding a large tooth embedded in stone, with no skeleton around it and no tracks nearby to provide context. Early researchers compared the tooth to animals they already knew. A large tooth suggested a large reptile. That seemed like the simplest explanation. In hindsight, the interpretation was wrong, but it was not foolish. It simply showed that the evidence had outrun the imagination. Teeth are particularly tricky clues because similar shapes can evolve in very different animals that eat similar foods. Only later, when more bones appeared and patterns began to emerge, did scientists realize that the tooth belonged to a completely different kind of creature. What once seemed like an odd curiosity became a crucial clue in a much larger puzzle. Moments like this are beautiful examples of how science progresses. A mistaken idea becomes a stepping stone toward a better understanding. The same stone that once caused confusion still holds the tooth that started the journey. The discovery of dinosaur fossils helped transform paleontology into a modern scientific discipline. Once these fossils became widely known, they demanded careful investigation. Understanding them required more than speculation or folklore. Scientists needed anatomy, geology, and systematic comparison. Each skeleton raised new questions. How old was the rock layer where it was found? What environment once existed there? What animals lived alongside it? Museums began treating fossils not simply as curiosities, but as scientific evidence. Specimens were cataloged with notes, maps, and measurements so that future researchers could study them again. Competition between fossil hunters also accelerated discovery. Rivalries pushed researchers to dig faster and search wider. Public fascination played its own role. Crowds flocked to see these ancient giants, and public interest helped fund further expeditions. Through this mixture of curiosity, rivalry, and careful study, paleontology matured. It became a science that tests ideas against evidence and revises conclusions when new discoveries appear. Dinosaurs, in many ways, became the proving ground for these scientific methods, and those methods continue to guide research today. Early museum displays often showed dinosaurs dragging their tails along the ground. When the first skeletons were assembled for public viewing, scientists had no living models to guide them. They often relied on comparisons with large reptiles, such as crocodiles. Those animals move with sprawling bodies and heavy tails that drag behind them. As a result, early dinosaur mounts were posed with tails resting on the ground like additional supports. Visitors loved these displays, and the image became deeply embedded in popular imagination. But the posture contained a subtle misunderstanding. A tail dragging through the dirt would leave constant marks. It would also strain joints and waste energy during movement. As more complete skeletons were discovered and fossil trackways were studied, scientists realized that this posture did not match the evidence. The tail was not meant to drag, it was meant to balance. This realization dramatically changed how dinosaurs were reconstructed. Later discoveries revealed that dinosaur tails were held high, acting as powerful balancing structures. A tail is not merely an extra appendage. It is an important counterweight, a steering tool, and a crucial part of maintaining balance while moving. When paleontologists examined dinosaur skeletons more closely, they began studying the joints, the scars where muscles once attached, and the stiffness of the tail vertebrae. All of these clues pointed to the same conclusion. The tail was meant to extend behind the body, lifted from the ground. In this position, it balanced the weight of the head and torso over the hips, allowing longer strides and quicker turns. It also meant the animal could move efficiently without scraping part of its body across the ground. Fossil trackways support this idea as well. Many preserved trails of dinosaur footprints show no sign of a tail dragging between the steps. The result is a much more dynamic picture of dinosaur movement. Predators appear like runners rather than crawling reptiles. Herbivores appear like steady travelers crossing long distances. A raised tail may seem like a small detail, but it completely transforms the silhouette of these animals. Suddenly, dinosaurs feel alive, balanced, alert, and ready to move. Modern technology has also revealed that fossils sometimes remain hidden inside solid rock long after discovery. In the past, preparing a fossil required slowly removing surrounding stone with tools. This process was careful but sometimes risky, especially when delicate structures were involved. Today, scientists can use advanced scanning technologies, such as CT imaging, to peer inside rock without breaking it apart. These scans can reveal bones buried deep within stone blocks, sometimes uncovering delicate structures that would crumble if exposed too quickly. This method has changed how discoveries happen. A fossil can now be studied while still safely protected within its rock shell. Researchers can plan their excavation more carefully, knowing exactly where bones are located. Scanning also allows scientists to explore the interior of fossils. They can detect tiny fractures, internal cavities, or unexpected shapes hidden within the rock. Sometimes these scans reveal astonishing surprises. A stone block thought to contain a single bone might actually hide an entire skull. In other cases, fossils from two different animals may be found intertwined inside the same rock. It is like switching on a light inside a sealed room. The rock stops being a barrier and becomes a window into the past. Bones themselves can record growth patterns similar to the rings of a tree. Inside many dinosaur bones, microscopic layers mark periods of growth and pause. These layers often form in response to seasonal changes in food availability or environmental stress. When scientists cut a bone into an extremely thin slice and examine it under a microscope, light can pass through these layers. The result is a record of the animal's development over time. These patterns do not always form simple yearly rings like those in trees. Different bones record different aspects of life, and the body can remodel bone tissue as the animal ages. Still, when the evidence is clear, these structures allow scientists to reconstruct a surprisingly detailed growth history. A skeleton becomes more than a static shape. It becomes the record of a life lived through changing seasons, years of abundance followed by years of hardship. Some bones show steady growth. Others reveal sudden surges in size or interruptions caused by illness or environmental stress. In this way, a dinosaur fossil becomes something very personal. It stops being just a specimen and begins to represent an individual that lived through real challenges. Teeth can also preserve chemical traces that reveal moments of stress during an animal's life. Teeth grow gradually, adding layers over time. Each layer can contain chemical signatures reflecting the conditions experienced by the animal. Periods of drought, harsh winters, or poor nutrition can leave detectable marks in these chemical patterns. By sampling along the length of a tooth, scientists can sometimes reconstruct a timeline of environmental stress. This is similar to reading a slow recording of the animal's life. Different chemical ratios may reveal changes in diet, shifts in water sources, or periods when growth was strained. These details bring ancient creatures closer to us. Stress is not an abstract idea. It represents hunger, exhaustion, or environmental hardship. Within a single tooth, scientists can sometimes detect the traces of a difficult season and the relief that followed when conditions improved. Fossilized skin impressions have revealed that many dinosaurs possessed intricate scale patterns. Bones provide the framework of an animal, but skin reveals how that body met the outside world. In rare cases, the outer surface of a dinosaur pressed into fine sediment before the body decomposed. Over time, the sediment hardened, preserving the texture of the skin. These impressions often show mosaics of small scales arranged in repeating patterns. Some areas appear tightly packed and fine, while others show larger, rougher scales, depending on how the skin needed to flex or resist wear. Seeing these textures transforms how we imagine dinosaurs. They cease to resemble smooth statues. Instead, they appear as living animals with textured skin, protective surfaces, and physical details shaped by everyday life. Skin impressions also guide both scientists and artists. They prevent wild speculation and remind us that much of every animal is normally lost to time. Whenever a fragment of skin survives, it feels almost like a handshake across millions of years. Some dinosaurs developed heavy armor plates that functioned like living shields. For animals that could not easily outrun danger, protection became the best defense. Armored dinosaurs evolved bony plates embedded within the skin, forming protective layers across their backs and sides. These plates could blunt bites, deflect claws, and make attacks far less rewarding for predators. Armor also changes how predators behave. A hunter approaching such an animal might hesitate, searching for a softer angle of attack. That hesitation alone might give the armored dinosaur time to escape. Some species developed armor patterns so distinctive that a single plate can identify the animal, almost like a fingerprint preserved in stone. Yet armor comes with a cost. Carrying heavy defensive structures requires strong muscles and constant energy. These dinosaurs were built like living tanks, supported by powerful legs capable of carrying their protective weight. Armor is not simply a feature. It is a lifestyle shaped by constant pressure from a dangerous world. Among the most extraordinary armored dinosaurs were the ankylosaurs. These animals carried massive clubs at the ends of their tails. For a predator stalking an ankylosaur, the greatest danger did not come from the animal's mouth. It came from its tail. The tail ended in a large, dense knob of fused bone. The rest of the tail was stiffened by reinforced vertebrae, allowing it to swing like a powerful club. Driven by strong hips and body weight, a single well-timed swing could deliver tremendous force. A strike powerful enough to break a predator's leg would be devastating. For a hunter that relies on speed to capture prey, a broken leg could mean starvation. The tail club was both weapon and warning. It announced that attacking such an animal would be risky. Creatures that appeared slow could suddenly become extremely dangerous. And danger has a way of earning respect in the natural world. Stegosaurus carried some of the most recognizable structures in the entire history of life, the tall plates rising along its back. These plates have fascinated scientists for generations because their exact purpose is still debated. One possibility is display. Large plates could make an animal appear bigger and more impressive, helping it signal strength to rivals or attract attention from potential mates. In open landscapes, such features could be seen from far away, turning the body itself into a kind of living billboard. Another possibility involves temperature regulation. The plates were filled with channels that likely carried blood close to the surface. If warm blood circulated through these structures, heat could be released into the surrounding air. In cooler conditions, the plates might also help absorb warmth from sunlight. Either way, the plates gave the animal a striking presence. Even standing still, a stegosaurus would have looked dramatic against the landscape. The shapes of the plates varied between species and even between individuals, suggesting that they may also have helped dinosaurs recognize members of their own kind. These plates were not simply decoration. They were signals written directly into the skeleton. Triceratops carried 3 horns and a broad, bony frill, giving it one of the most iconic silhouettes of any dinosaur. At first glance, this headgear looks like pure weaponry, and certainly the horns could serve as formidable defensive tools against predators. A charging Triceratops would have been a dangerous opponent, yet horns in modern animals often serve multiple purposes. In many living species, horns and antlers help settle disputes over mates and social rank. These contests can be intense, but they are often ritualized rather than lethal. Fossil skulls of Triceratops sometimes show signs of healed injuries. These marks suggest that individuals survived heavy impacts and continued living afterward. This evidence hints at a world where clashes occurred regularly, where strength and courage played roles in social life. The frill behind the skull added yet another layer of meaning. It protected the neck, but it also expanded the animal's visual profile. A large frill could make an individual appear more impressive or intimidating during displays. Imagine 2 massive animals facing one another across dusty ground. Their heads tilt slightly. Their horns align. Dust swirls in the air as they measure each other before the moment of impact. Horns are not only tools of violence, they are also instruments of negotiation, display, and social structure. Among the most fascinating dinosaurs were the duck-billed hadrosaurs. Many species possessed elaborate crests on their heads. Inside some of these crests were hollow chambers connected to the nasal passages. These chambers may have functioned like musical instruments. Air passing through them could create resonating sounds, perhaps allowing dinosaurs to communicate across long distances. In wide landscapes where herds spread out while feeding, sound can travel farther than sight. A distinctive call might help individuals remain connected, warn others of danger, or signal that it was time to regroup. Such sounds might also help young dinosaurs locate adults. In a busy, crowded environment, a recognizable call could guide hatchlings back to safety. The crest, therefore, becomes more than decoration. It becomes a tool for belonging. Different crest shapes could produce different tones, allowing species to distinguish one another even when several herds shared the same habitat. Imagine standing in an ancient floodplain as a distant call echoes across the open land. You are not simply hearing noise. You are hearing the social life of dinosaurs carried on the wind. One of the most famous crested dinosaurs was Parasaurolophus. Its long, curved crest extended far behind the skull, forming a remarkable hollow structure. Scientists believe that air passing through this crest could produce deep, resonant sounds. Low tones travel especially well through forests and uneven landscapes. If Parasaurolophus lived in groups, such calls might have helped coordinate movement across long distances. A deep honking sound could keep the herd together or signal danger without requiring constant visual contact. It may even have carried individual signatures, unique sounds that allowed animals to recognize one another. The crest also made the animal instantly recognizable. In crowded environments where quick decisions mattered, such distinctive shapes could prevent confusion between species. Communication itself shapes behavior. When one animal calls, others respond. A scattered group can suddenly reorganize into a coordinated movement. In that way, sound becomes survival. Coordination reduces panic. It keeps young animals close to adults. It helps groups move together like a single living system. The anatomy of the crest may have turned Parasaurolophus into a living musical instrument, one that helped maintain order in the herd. Some dinosaurs possessed thick, dome-shaped skulls. These animals, known as pachycephalosaurs, appear to have had heads built for impact. At first glance, their rounded skull domes suggest dramatic headbutting behavior similar to modern animals such as bighorn sheep. Yet the reality may have been more subtle. The dome could certainly withstand powerful impacts, but it might also have supported pushing contests where balance and strength mattered as much as speed. Displays of strength often involve physical contact, even when serious injury is not the goal. The skull itself was reinforced, and powerful neck muscles would have helped absorb shocks. If pachycephalosaurs did collide head-to-head, the behavior may have been related to social rank, territorial disputes, or competition for mates. In that sense, the dome was not merely armor. It was a social signal. It told rivals something important. I am strong enough to withstand the impact. In nature, that kind of demonstration can carry meaning even before any fight begins. Spinosaurus represents one of the most unusual dinosaur body plans discovered so far. Unlike many predators, Spinosaurus appears to have been adapted for life near water. Its long, narrow snout resembled that of modern fish-eating animals. Recent fossil discoveries also revealed a broad, paddle-like tail that may have helped propel the animal through water. This changes how we imagine its hunting behavior. Rather than chasing prey across open land, Spinosaurus may have spent much of its time along rivers and wetlands, searching for fish. Picture a predator standing quietly at the edge of a prehistoric river. Suddenly, the water erupts as powerful jaws snap shut around a struggling fish. A semi-aquatic lifestyle would influence everything from movement to balance. It might also explain why Spinosaurus fossils are often found in sediments that formed in ancient river systems. The existence of such animals reminds us that dinosaurs explored many different lifestyles. They were not confined to a single ecological role. Evolution takes advantage of opportunity, and water offers endless possibilities. Some theropod dinosaurs possessed large, curved claws shaped almost like sickles. These claws were not simply sharp, they were hooks designed to hold on to prey that struggled and fought back. In several species, the enlarged claw on the foot may have helped pin prey to the ground while the jaws delivered the killing bite. This suggests a hunting style that involved close contact and intense physical struggle rather than a single distant strike. Using the foot as a weapon requires extraordinary coordination. A predator must maintain balance while its prey twists, kicks, and attempts to escape. Strong legs, flexible joints, and rapid reflexes would all be necessary to control such chaotic encounters. In this sense, the anatomy of these dinosaurs becomes a kind of choreography. Every part of the body works together in a coordinated moment of action. The curved claw may also have served additional purposes. It might have helped animals climb, grip uneven surfaces, or scramble through difficult terrain. When you imagine the instant of contact between predator and prey, you can almost feel the precision involved. A well-placed claw could turn confusion into control, and control is what every predator seeks. Many of these fast predators also relied heavily on their tails for balance. The tail of a raptor was not loose or flexible like a rope. Instead, it was reinforced by specialized bones that stiffened much of its length. This structure allowed the tail to function almost like a balancing pole. Think of a tightrope walker carrying a pole to maintain stability. The tail served a similar role, keeping the animal balanced during sudden turns, leaps, and rapid stops. Such agility would be crucial in environments filled with obstacles, forests, rocky terrain, or dense vegetation where prey could vanish in seconds. Landing from a jump requires careful control. A bad landing could mean injury, and injury could mean death. A stiff tail helped the entire body operate as a coordinated system. Head, torso, and legs align together during movement. This is one reason raptors feel so vivid in our imagination. Their bodies resemble those of athletes. Every structure exists to support motion, and motion itself becomes a strategy for survival. Dinosaurs often traveled in groups, leaving behind parallel trails of footprints. When multiple trackways appear side by side in the same rock layer, they reveal animals moving together rather than separately. This behavior likely offered many advantages. Groups can detect predators sooner because more eyes scan the landscape. They can also protect younger members who remain safer within the center of the herd. Trackways sometimes include prints from individuals of different sizes. This suggests that adults and young animals traveled together. Such evidence hints at family groups rather than random gatherings. Movement itself becomes a form of communication. Animals in a herd must adjust their pace, direction, and spacing in response to the others around them. A coordinated group can move almost like a single organism. The fossilized footprints record these silent decisions. Step by step, they preserve a moment when many lives move together across a landscape that has long since vanished. Trackways can also reveal how dinosaurs moved. The distance between footprints shows the length of each stride. The depth and shape of each print can hint at the force of the step. If the path curves sharply, it suggests the animal pivoted rather than simply drifting. For large animals, sharp turns require significant balance and control. Sometimes footprints grow farther apart, indicating the animal accelerated from a walk into a run. Even the direction of claw marks can reveal how the foot pushed against the ground. Researchers compare these ancient traces with tracks left by modern animals. By applying physics and biomechanics, they reconstruct how these creatures once moved. A trail of footprints becomes a performance frozen in stone, and the performer is an animal that once moved across the earth with purpose. Occasionally, fossil trackways show signs of injury. A pattern of footprints may reveal uneven spacing or unusual angles in the steps. If this irregular pattern repeats again and again, it may indicate that the animal was limping. This discovery tells a powerful story. An injured dinosaur continued walking long enough to leave behind a trail. It survived at least for some time after the injury occurred. Perhaps it moved more slowly. Perhaps it stayed closer to companions for protection. Each step recorded in stone represents a decision to keep moving despite pain. The fossil record rarely captures emotion, but a limping trail of footprints carries a sense of determination. The predator that caused the injury may be gone. The struggle itself may have vanished without leaving any other trace. Yet the trackway remains, a stubborn record of life continuing one step at a time. Some of the most revealing fossils are not bones at all. They are fossilized droppings known as coprolites. Although they may seem unglamorous, coprolites offer some of the most direct evidence about what ancient animals actually ate. Inside these fossils, scientists sometimes find fragments of bone, plant material, fish scales, or other recognizable remains. A carnivorous dinosaur's coprolite may contain crushed bone fragments, showing that its digestive system could process hard material. An herbivorous dinosaur's coprolite might preserve plant fibers that reveal the types of vegetation it consumed. These discoveries provide details that skeletons alone cannot reveal. Coprolites offer evidence from the inside out. They record the daily meals of animals that lived millions of years ago. Sometimes coprolites preserve surprisingly complex contents. Fish scales can indicate hunting near water. Bone fragments might reveal scavenging behavior as well as active predation. Plant fibers can show how tough vegetation passed through the digestive system. Each tiny fragment is a clue. Once it belonged to a living organism. Then it was eaten, digested, and finally preserved as part of the fossil record. Even something as ordinary as digestion becomes a window into ancient ecosystems. Some dinosaurs swallowed stones to help grind tough plant material inside their stomachs. These stones, known as gastroliths, acted like an internal grinding tool. Animals that do not chew extensively with their teeth may rely on muscular stomachs and swallowed stones to break down fibrous food. Over time, the stones become smooth and polished from constant friction inside the digestive system. When paleontologists find clusters of such stones near dinosaur skeletons, they sometimes interpret them as remnants of this internal grinding system. This method of digestion allows animals to swallow large quantities of plant matter quickly. The real processing happens later, inside the body. In this way, the dinosaur's stomach becomes a kind of biological mill. Food is crushed, mixed, and broken down into nutrients that fuel the enormous body. Feeding, in this sense, is not only about teeth. It is about the entire digestive system working together. Some herbivorous dinosaurs may even have swallowed grit to assist with digestion. Fine sand or small stones could help shred tough plant material, allowing nutrients to be extracted more efficiently. This strategy still appears in many modern animals today. It allows herbivores to process plants that might otherwise pass through the body without releasing their energy. Evolution often favors simple solutions that work reliably, and sometimes the simplest tools, even small stones, can play a powerful role in survival. The long necks of sauropods allowed them to browse across wide areas without constantly moving their massive bodies. A long neck is not only useful for reaching high branches, it also allows an animal to reach far in many directions while remaining in one place. With a sweeping arc of movement, a sauropod could feed across a large circle of vegetation without taking a single step. For an animal that weighed many tons, reducing unnecessary movement would have saved enormous amounts of energy. This efficiency may also have helped several large herbivores feed in the same area without competing directly. Instead of crowding shoulder to shoulder, different individuals could reach different patches of plants simply by extending their necks in different directions. Of course, such long necks came with challenges. Blood had to be pumped upward to reach the brain. Muscles had to control and stabilize the long structure with remarkable precision. Yet the very existence of these animals proves that evolution found workable solutions. Their bodies suggest a quiet kind of strength, a lifestyle based on patience, reach, and the steady conversion of plants into energy. Some herbivorous dinosaurs may also have relied on fermentation inside enormous digestive systems. Many plants contain tough fibers made of cellulose. Most animals cannot digest cellulose directly. Instead, certain herbivores rely on communities of microorganisms living in their digestive systems. These microbes break down plant material through fermentation, releasing nutrients that the host animal can absorb. Large dinosaurs with enormous torsos may have housed long digestive tracts filled with such microbial communities. In this system, digestion becomes a slow and continuous process. An animal can eat quickly, then allow the internal ecosystem of microbes to break down the food gradually. Fermentation can generate heat and chemical energy, turning tough plant matter into usable nutrients. This method of digestion may help explain how gigantic herbivores survived on vegetation that might appear relatively low in nutritional value. Their bodies functioned almost like living bioreactors. Within their enormous bellies, unseen organisms quietly transformed leaves and stems into strength. Dinosaurs also shaped their ecosystems in ways similar to large animals today. Consider how elephants influence African savannas. When very large animals move through a landscape, they do more than simply live in it. They transform it. Herds of massive herbivores can flatten vegetation and create pathways that other animals follow. Feeding can open clearings that allow sunlight to reach the ground, encouraging new plant growth. Predators influence where herbivores feel safe grazing, which in turn shapes patterns across entire ecosystems. Even nests, burrows, and feeding grounds can alter soil and water flow. Dinosaurs lived in great numbers for millions of years. Their presence would have shaped landscapes across the planet. A dinosaur was not simply an animal living within an ecosystem. It was an architect helping to shape that ecosystem. To imagine the dinosaur world properly, we must picture landscapes responding to their presence. Plants, rivers, and other animals would have constantly adjusted to the activities of these dominant creatures. The environment was not merely a stage. It was a dynamic system in which dinosaurs played central roles. The world of dinosaurs also experienced dramatic climate shifts. Periods of warmth allowed lush vegetation to spread across large regions. Later phases of cooler or drier climates altered the types of plants that could survive. Sea levels rose and fell repeatedly during the dinosaur era. Lowlands were sometimes flooded by shallow inland seas. Later, as waters retreated, new land surfaces emerged. These changes constantly reshaped dinosaur habitats. Populations that once roamed across continuous plains could become separated by rising seas or wetlands. Later, when water levels dropped, those populations might reconnect. Such shifting environments encouraged evolutionary change. Isolation can lead to new species forming. Reconnection can introduce competition and new ecological pressures. Dinosaurs lived through these slow yet powerful transformations. Their survival depended on flexibility. The map of their world never remained the same. Another immense force shaping dinosaur evolution was continental drift. During the age of dinosaurs, the continents slowly moved across the surface of the planet. Land masses that were once connected gradually separated. Others drifted closer together. These movements changed migration routes and isolated populations. Isolation is a powerful engine of evolution. When groups of animals become separated, they face different environments, different predators, and different opportunities. Over millions of years, such separation can produce entirely new species. Mountains may rise, climates may shift, and new land bridges may appear between continents. Dinosaurs evolved on a planet whose geography was constantly changing. Their story is inseparable from the slow movement of the Earth's crust. Even the ground beneath their feet was reshaping the future. Interestingly, fossils found in modern deserts often come from places that were once wetlands. Today, these landscapes appear dry and barren. Yet millions of years ago, many were rich river plains filled with vegetation and wildlife. Wetlands are especially good environments for fossil preservation. Floods can rapidly bury animals beneath layers of sediment. Fine mud can seal remains away from scavengers and oxygen. Over vast stretches of time, those wetlands may dry out, rise above sea level, and eventually erode into desert landscapes. The fossils remain hidden until wind and erosion expose them again. A dinosaur skeleton discovered among desert sands may once have lived beside lush rivers filled with fish, turtles, and thick vegetation. Paleontologists learn to read rocks like ancient diaries. Ripple marks in stone may record flowing water. Cracked mud layers may show ancient drought. Mineral patterns can reveal how the environment changed long after the animals vanished. In this way, fossils tell stories not only about the animals themselves, but also about the worlds they inhabited. Even Antarctica once held forests where dinosaurs walked. This idea may seem surprising, yet fossil evidence shows that parts of Antarctica supported forests during portions of the dinosaur age. The continent was located farther north at the time, and global climates were different from today. Fossil plants discovered in Antarctic rocks reveal ecosystems capable of supporting complex food webs. Dinosaurs moving through these forests would have experienced environments that challenge our modern expectations. Antarctica today symbolizes ice and isolation, yet deep in its geological past, it was a land of trees, soil, and life. This realization reminds us how dramatically Earth can change. The planet we know today is only one moment in a much longer story. Dinosaurs living in southern forests would have faced seasonal changes in light and temperature. They may have experienced long periods of dim winter daylight. Surviving under such conditions required resilience. These discoveries expand the map of dinosaur life. They show that dinosaurs inhabited environments far beyond the stereotypical warm jungles often imagined. Their world was broader, more varied, and far more dynamic than we once believed. Some dinosaurs lived in regions where winter brought long periods of darkness. At high latitudes, the sun can disappear below the horizon for months at a time. Living in such places requires special strategies. Darkness makes it harder to find food, avoid predators, and navigate the landscape. Dinosaurs that remained in these regions during polar winters may have relied on several adaptations. They might have stored energy during the brighter seasons. They may have changed their diets when certain plants became scarce. Social behavior could also have helped, with groups providing protection and shared awareness of danger. In prolonged darkness, senses other than vision become especially important. Sound and smell may guide movement when light is limited. Some species may have migrated seasonally to avoid the harshest conditions. Others may have endured the long winter nights in place, much as many animals do in modern polar environments. Fossil discoveries in these regions suggest that dinosaurs were indeed present and active there. The idea of dinosaurs surviving months of darkness adds another dimension to their story. It reminds us that their world included challenges that required resilience and adaptability. Scientists can sometimes estimate ancient body temperatures by studying the chemistry of fossil bones. Certain minerals within bones and teeth preserve chemical signatures that formed while the animal was alive. These signatures can sometimes reflect the temperature conditions inside the body at the time the tissue formed. In essence, parts of the skeleton can act as a kind of ancient thermometer. Understanding body temperature is important because it relates to metabolism, endurance, and activity levels. Animals with higher internal temperatures often maintain more consistent energy levels. They can remain active for longer periods and recover more quickly after exertion. Studying these chemical patterns requires careful work. Fossils may undergo changes after burial, and scientists must distinguish original biological signals from later geological alterations. When the evidence holds, however, it provides valuable insight into dinosaur physiology. Instead of seeing only the shapes of bones, researchers can begin to understand how these animals functioned as living organisms. Many dinosaurs may have had higher metabolisms than traditional reptiles. A higher metabolism acts like a stronger engine inside the body. It allows sustained movement, faster growth, and quicker responses to environmental challenges. Several lines of evidence point in this direction. Bone structures often show signs of active lifestyles. The close evolutionary relationship between birds and certain dinosaur groups also supports the idea of energetic metabolism. An active metabolism would help explain how dinosaurs thrived across many different environments, including cooler climates where sluggish animals might struggle. This perspective changes the way we imagine a dinosaur's daily life. Rather than waiting for sunlight to warm their bodies, many dinosaurs may have been capable of early activity and long-distance movement. they could travel farther in search of food and respond more quickly to danger. Of course, not every species would have shared the same metabolic rate. The diversity of dinosaurs suggests a range of physiological strategies. Still, the growing body of evidence paints a picture of animals far more dynamic than the outdated image of slow, lethargic reptiles. During the age of dinosaurs, flowering plants began to spread across the world. These plants introduced new forms of vegetation, leaves, fruits, and seeds with different chemical properties than older plant groups. As flowering plants expanded, they reshaped ecosystems. Herbivorous dinosaurs may have encountered new feeding opportunities. Some species adapted to browse on these emerging plants, while others continued relying on older vegetation such as ferns and conifers. Changes in plant communities ripple through entire ecosystems. When the available plants change, the animals that depend on them must also adapt. Some move to new habitats. Others evolve new digestive strategies. Some disappear altogether. The spread of flowering plants did not occur instantly or uniformly across the globe. Instead, it unfolded gradually over millions of years. Dinosaurs lived through this quiet botanical revolution, their diets and habitats slowly shifting as new plants appeared beneath their feet. In this way, plant evolution helped shape dinosaur diversity just as much as claws, teeth, or horns. Insects also played an important role in these ecosystems. Ancient landscapes were filled with small creatures buzzing, crawling, and burrowing through vegetation. Insects chewed leaves, tunneled into wood, and carried pollen from plant to plant. Pollination is a subtle process, yet it profoundly influences plant reproduction and distribution. As plants diversified, insect activity helped them spread across new territories. These botanical changes then influenced where herbivores could thrive. Small dinosaurs and early birds may have fed on insects, creating intricate food webs within the undergrowth. This reminds us that the dinosaur world was not simply a land of giants. It was a complex ecosystem filled with countless smaller interactions. Tiny creatures shaped the plants. Plants shaped the herbivores. Herbivores shaped the predators. All of these relationships formed a dynamic, living network. Natural disturbances also played an important role in shaping dinosaur habitats. Wildfires could sweep through forests, clearing old vegetation and releasing nutrients into the soil. After a fire, new plants often grow rapidly, attracting herbivores seeking fresh growth. Storms could flatten forests, redirect rivers, and deposit fresh layers of sediment. These events sometimes buried animals in tracks beneath mud, preserving them as fossils millions of years later. Floods may have carried bodies into river channels where sediment protected them from decay. The landscapes of the dinosaur world were not static. They were constantly reshaped by storms, fires, and shifting waterways. Each disturbance created both danger and opportunity. For dinosaurs, survival meant adapting to these changing conditions again and again. Even the brains of dinosaurs reveal interesting clues about their lives. Many species had relatively small brains compared with their body size. Yet brain size alone does not determine complexity of behavior. Different animals evolve brains suited to the challenges they face. Many dinosaurs required strong instincts, rapid reactions, and reliable balance more than complex planning. A herd animal must recognize danger instantly and move with the group at the right moment. A predator must judge distance and timing during a hunt. These tasks rely on specialized neural circuits rather than large brains devoted to abstract thinking. Modern animals demonstrate similar patterns. Crocodiles, for example, possess relatively small brains, yet remain highly effective predators. Dinosaurs likely relied on a combination of senses, reflexes, and coordinated movement. Their intelligence may have been specialized rather than generalized. In some species, brain regions associated with balance and coordination appear relatively enlarged. This suggests that certain dinosaurs possessed remarkable agility. Maintaining balance during rapid movement requires constant adjustments. A running animal must stabilize its head and vision while the body bounces and twists with each step. These abilities become especially important for predators that leap, turn sharply, or navigate uneven terrain. Enhanced coordination would allow such animals to move with precision. In this way, dinosaurs were not simply massive creatures lumbering through ancient landscapes. Many were capable of quick, controlled motion that required careful neural control. Large eyes in some dinosaurs suggest that certain species may have been active in dim environments. Eyes are costly organs for the body to build and maintain. Evolution rarely enlarges them without a clear advantage. Large eyes gather more light. This ability improves vision in twilight, dense forests, or nighttime conditions. Such adaptations change how we imagine dinosaur behavior. Instead of living only under bright daylight, some species may have been active during cooler evening hours or in shadowed environments beneath thick vegetation. A predator moving through the forest at dusk could approach prey with greater stealth. A smaller dinosaur might forage safely when larger hunters were less active. Eye placement also matters. Forward-facing eyes can improve depth perception, allowing predators to judge distance accurately during leaps or strikes. Eyes placed more to the sides of the head provide a wider field of view, helping prey animals detect danger approaching from multiple directions. Each arrangement reflects a different strategy for survival. In addition to vision, the inner ear structures of dinosaurs reveal clues about how they sensed movement. Deep within the skull lies a system of canals responsible for detecting motion and balance. These canals help animals track the orientation of their heads in space. They detect acceleration, tilting, and turning, constantly informing the brain how the body is moving. Fossil skulls sometimes preserve the shape of these canals. By studying them, scientists can estimate how sensitive an animal's sense of balance may have been. Animals that move quickly or navigate complex environments tend to possess more responsive systems. Such sensitivity allows the head to move rapidly without losing stability. It helps a predator track moving prey, avoid obstacles, and strike with precision. In essence, the inner ear helps transform motion into coordinated action. When scientists reconstruct these structures, they are examining a hidden system that guided every movement the animal made. Some dinosaurs may also have been capable of hearing very low-frequency sounds. Low sounds travel long distances and can pass around obstacles more effectively than high-pitched noises. If dinosaurs produced and detected such sounds, their communication may have carried across forests, valleys, and open plains. Large animals often generate deeper vocal tones because of their size. These sounds could help maintain contact between members of a herd spread across wide areas. Low-frequency calls might also serve as early warnings. A distant rumble or resonant call could signal the approach of another group or the presence of danger. This possibility suggests that dinosaur environments may have been filled with deep, resonating calls. Instead of the sharp chirps common among many modern birds, the prehistoric landscape may have vibrated with slower, powerful sounds. These voices could travel through the air and even through the ground. Communication likely played an important role in coordinating movement across large floodplains. A herd traveling together must remain organized while feeding, watching for predators, and navigating obstacles. Short signals might mean, "Stay together." Longer calls might warn of danger. Repeated sounds could help young animals remain close to adults when tall vegetation or dust limited visibility. Communication transforms a group of individuals into a coordinated community. A scattered herd can quickly reorganize when calls guide movement. You can imagine the moment. One animal calls, others respond. Gradually, the entire group shifts direction like a slow-moving tide. Such signals would act as the glue holding social groups together. They would turn travel into a shared effort for survival. Distinctive crests, horns, and head shapes may also have helped dinosaurs recognize one another. In crowded environments, quick identification matters. If an animal cannot easily distinguish friend from rival or adult from juvenile, it wastes valuable time and energy. Visual signals allow individuals to recognize members of their own species instantly. These features may also help identify particular individuals within a group. Many modern animals recognize familiar faces, markings, or silhouettes. Dinosaurs may have relied on similar cues. A dramatic crest or horn arrangement could communicate maturity, strength, or social status. Such features reduce unnecessary conflict and help maintain stable social relationships. They allow animals to understand who dominates, who belongs, and who is safe to approach. These structures were not only tools for defense, they were also tools for social order. Fossils sometimes reveal healed injuries, proving that dinosaurs could survive wounds and recover. Some skeletons show fractures that healed during the animal's lifetime. Others preserve bite marks surrounded by new bone growth. Healing takes time. An injured animal must continue feeding, avoiding predators, and navigating its environment while the body repairs itself. These fossils remind us that dinosaurs lived through hardship. They were not always victorious predators or untouchable giants. Many were survivors. A healed injury hints at resilience. Perhaps the animal changed its hunting strategy. Perhaps it stayed closer to companions for protection. Even solitary animals must adapt when wounded. The fossil record often appears as a collection of endings, yet healed injuries represent continuation. They show that life persisted beyond moments of violence. Sometimes, bite marks preserved in bone reveal predator attacks that failed. The predator struck. The prey escaped. Weeks or months later, the bone healed. These marks capture a dramatic moment that might otherwise have vanished from history. Predation is never guaranteed. Every hunt carries risk for both hunter and hunted. A missed attack wastes energy. A wounded predator may lose its ability to hunt. A prey animal that escapes must survive the recovery period. When scientists find healed bite marks, they glimpse a moment of struggle frozen in stone. The predator is gone. The chase is gone. What remains is the quiet evidence of survival. Rare fossils sometimes preserve evidence of disease. Certain dinosaur bones display abnormal growths that resemble tumors found in modern animals. These discoveries reveal that dinosaurs faced internal health challenges as well as external dangers. Disease, injury, and biological malfunction are part of life. Even the giants of prehistory were not immune. Such fossils humanize these ancient animals in unexpected ways. They remind us that dinosaurs were living organisms with bodies that could break, heal, and sometimes fail. Occasionally, fossils preserve soft tissues such as skin outlines or muscle impressions. Normally, these tissues decay rapidly. But under exceptional conditions, rapid burial, low oxygen, fine sediment, delicate structures can survive as impressions or mineralized films. These fossils reveal textures and shapes that bones alone cannot show. They allow scientists to reconstruct how muscles attached, how skin stretched across the body, and how feathers or scales were arranged. Suddenly, the animal feels more real. Not just a skeleton, but a living body. Some dinosaurs were buried in volcanic ash, preserving remarkable detail. When volcanic eruptions spread fine ash across landscapes, animals caught in the event can be rapidly covered and sealed away. Later, this ash hardens into rock, preserving entire scenes. Plants, tracks, and animals may all appear within the same layer. Such sites offer snapshots of ancient ecosystems. They capture a moment in time, a single day in a vanished world. Amber provides another extraordinary window into the past. When tree resin hardened into amber, it sometimes trapped small objects, insects, plant fragments, and even tiny feathers. These delicate fossils preserve details far too small to survive in other conditions. A feather trapped in amber may still show microscopic structures that once held pigment. Scientists studying these structures can sometimes infer ancient colors. Melanosomes, tiny pigment bodies, can survive inside fossil feathers. Their shapes and arrangements resemble those found in modern birds. From these structures, researchers may estimate whether feathers were dark, reddish, or patterned. Color suddenly becomes part of the dinosaur story. Dinosaurs were not gray statues. They may have displayed blacks, browns, and rusty reds across their bodies. These colors could provide camouflage or visual signals. Even eggs sometimes preserve embryos. Inside certain fossilized eggs, tiny skeletons appear curled in positions similar to modern bird embryos preparing to hatch. These discoveries reveal how young dinosaurs developed before birth. They also link eggs to specific dinosaur groups. For a moment, the fossil record shows life at its very beginning. A dinosaur embryo waiting quietly inside its shell. Brain cases occasionally preserve impressions of the brain itself. Although brains rarely fossilize, the interior of the skull can retain shapes reflecting brain structures. Sometimes, minerals fill these spaces, forming natural casts. These casts reveal the outlines of regions responsible for smell, vision, and coordination. While they cannot show thoughts, they offer valuable clues about sensory priorities. They allow scientists to estimate how animals sensed the world around them. Teeth can even preserve chemical traces of the water dinosaurs once drank. Different water sources carry distinct chemical signatures. These signatures can become locked into tooth enamel as it forms. By analyzing these signals, scientists can sometimes determine where an animal lived or whether it migrated between regions. A single tooth may carry the memory of ancient rivers or lakes. Dinosaurs did not live alone in their world. Early mammals already existed, living quietly alongside them. These mammals were typically small, quick, and cautious. Many likely lived nocturnal lives, emerging at night when large predators were less active. They fed on insects, plants, and small animals. Their strategy was survival through secrecy. This long coexistence lasted millions of years. In many ways, dinosaurs created the evolutionary pressure that shaped early mammal traits such as keen hearing and strong senses of smell. When the Great Extinction eventually came, mammals were prepared to adapt. Birds, meanwhile, had already begun evolving while dinosaurs still thrived. Flight did not suddenly appear after dinosaurs vanished. It developed gradually within certain dinosaur lineages. Early birds shared ecosystems with feathered dinosaurs that could glide or leap but not yet fly efficiently. The boundary between bird and dinosaur is therefore wonderfully blurred. Fossils such as Archaeopteryx show a mix of features: wings and feathers alongside teeth and clawed fingers. These transitional animals reveal evolution in motion. Nature does not draw clear lines. Instead, it modifies existing forms step by step. Birds are not replacements for dinosaurs. They are their surviving descendants. Every sparrow, eagle, or pigeon carries a living connection to that ancient lineage. When a bird hops across a sidewalk, it brings with it echoes of forests and floodplains that existed millions of years ago. Dinosaurs did not completely vanish. They changed. Their legacy still surrounds us, and that is where our journey gently comes to rest. You have traveled tonight across immense stretches of time, through forests that no longer stand, across plains shaped by rivers and fire. You have met giants whose footsteps once shook the ground, and smaller creatures that lived quietly in their shadows. You have seen how life rises, changes, struggles, and continues. The age of dinosaurs may feel distant, yet its echoes remain close, in feathers, in birdsong, and in the living world outside your window. If you are still awake and curious, another video is waiting on the screen to guide you into another peaceful exploration. And if these quiet journeys bring you comfort, you are always welcome to like, subscribe, or leave a gentle thought below so that others may find their way here as well. But for now, there is nothing left to do. Let your breathing slow. Allow the images of ancient worlds to soften and drift away. You have traveled across millions of years tonight, and now it is perfectly fine to rest. Sleep well. Good night.